right, today we're going to be taking a look at improper integrals and remind you that there is only one condition to the first fundamental theorem of calculus. If a function is continuous on the closed interval, that's the problem right there. If a function is continuous on the closed interval from a to b, which is saying closed interval and then giving you an interval notation with square brackets is actually redundant. And f, capital F, is the antiderivative of lowercase f on the interval from a to b. Then the definite integral from a to b of f of x dx is equal to f of b minus f of a. Basically, right, just the formula we learned in the beginning of chapter 4. So we're going to be looking at 3 examples today. Just to make this fit within a period, I have another video where I've got two more examples in it, including where we have a lower limit and upper limit that are both infinity, and another example that involves integration by trigonometric substitution. But we have 3 cases of recognizing that we have an improper integral where one of our limits is one of or both of our limits is equal to infinity. Our third example is also going to be an improper integral, and we're not going to see this infinity in the location of either an upper, lower, or both of those limits. But if you do have a definite integral where from a to infinity of f of x dx, that is going to be equal to the limit as b approaches infinity of the definite integral from a to b of f of x dx. But we're working around that condition of f needs to be continuous on a closed interval by recognizing that either when we have a limit that is infinity or negative infinity, or both limits are infinity, or like in example 3, we have a definite integral that has constant limits, but one of those limits are going to be located at a vertical asymptote. We're going to get around that condition failure of the function being continuous on a closed interval by introducing a upper limit of b when our upper limit is infinity, and change our definite integral into a limit statement. If we have a definite integral from negative infinity to b of f of x dx, where we have, again, here we have in our lower limit a negative infinity, that is not a closed interval. So we're going to introduce a lower limit of a, and then have a definite integral from a to b of f of x dx, but we're going to be taking the limit as a approaches negative infinity once we finish that integration. If you have a problem, and I don't believe I gave you any of these in the homework, but if it happens to be like, when you're retaking calculus or going into Calc 3 in college, if you have a lower and upper limit that are both infinity, the definite integral from negative infinity to infinity of f of x dx, what you're going to do to create that closed interval condition for the first fundamental theorem of calculus, you're going to introduce any constant, and I would recommend probably just using 0, but introduce a constant that is going to be convenient to work with for your particular integrand, and make your one definite integral with both the lower and upper limits being some form of infinity into 2 definite integrals, where you're going from, we have a definite integral from negative infinity to c, that will commonly just be 0, of f of x dx, plus, and then add that with another definite integral, now the lower limit being that same constant c, to an upper limit of infinity, and that's going to be of f of x dx. So that you can get the infinities out of the location of the upper and lower limit, and have the limit as a approaches negative infinity of the definite integral from a to c of f of x dx, plus the limit as b approaches infinity of the definite integral from c to b of f of x dx. And we're going to be looking for these limits to give us a real solution, a real finite solution. If we do, we get this idea. The definite integral converges, which means the definite integral, the limit, gives you a real finite solution if all limits exist. Our examples are only going to involve one limit, but you could potentially have 2. Otherwise, the definite integral is said to diverge. When we get into chapter 9 and we start talking about Maclaurin and Taylor series, we'll be looking at, in polynomials, we'll be looking and saying the language of convergence and divergence a lot. If you analyze a limit, you get a real finite solution, and that limit converges. If you get infinity or negative infinity, that limit is going to be said to diverge. For our first example, we're going to be taking a look at the definite integral from 1 to infinity of 4 times x to the negative 4 dx. So you can see right away that this definite integral is improper by the fact that one of the limits are infinity. We're going to be using this really strict notation of improper integrals where we take the infinity out of the location of either the upper or lower limit and introduce that limit statement, thus creating a definite integral, a true definite integral from a to b, and then holding that to that condition of f needing to be continuous on a closed interval. So we have the limit as b approaches infinity of the definite integral from 1 to b of 4 times x to the negative 4 dx. So we have the limit as b approaches infinity of, well, what's the integral of x to the negative 4th? X to the negative 3rd, and then you divide by negative 3. But of course, you have that multiple of 4 that's already out there with an upper limit of b and 1. So we have the limit as b approaches infinity of negative 4 over 3 times b. I'm bringing this x with the negative exponent down, and then so I can write that as a positive exponent. And so we have the negative 4/3. We have the x to the negative 3 coming down, but then I'm plugging in the upper limit of b, then minus a negative 4/3 times, which is now 1 cubed. And as we let b go to infinity, negative 4 over 3 times infinity is what? It's going to approach, well, the denominator is going to approach infinity, which means that's going to approach 0, yes. And then we have minus a negative, so plus 4 over what? 4 over 3. Thus, our answer is 4/3. That is a real finite limit. So this improper integral is said to converge, which just simply means you get a real solution. So the definite integral from 1 to infinity of 4 times x to the negative 4th dx is equal to negative 4/3. So we're just changing that notation on the definite integral so that we don't have an open interval, we have a closed interval, and that limit notation out front is allowing that b to approach infinity. And we're evaluating these questions using the proper, perfect definition of the first fundamental theorem of calculus, passing all the conditions, which is the function is continuous on the closed interval. Okay, so for another example, we have a definite integral, same limits, lower limit of 1, upper limit of infinity. We have this time 2 times x to the negative 1/5 dx. Try this one on your own. All right, who's helping me out? Awesome. We got the limit as b approaches infinity of the definite integral from 1 to b of 2 times x to the negative 1/5 dx. If you do want to move this 2 out in front of the limit statement, you can do that as well. What'd you do next?
Then I rewrote it using that fundamental theorem of calculus. So the limit b approaches infinity of 2 times b to the 4/5.
Negative 1/5 plus 1 is 4/5. And instead of dividing by 4/5, you probably multiply by 5/4 with that upper limit of b and 1. So we've got the limit as b approaches infinity of, I'm going to go ahead, actually, you know what I'm going to do? I'm going to take this 5/2 and move it out in front of the limit statement, not because we're almost done and I know you have the right answer, but just to kind of show that you can. And at certain times, bringing out those constant coefficients are going to make your, will make your arithmetic to simplify at the end easier. So we have 5/2, right? 2 divided by 4 is 1/2, times the limit as b approaches infinity of b to the 4/5 minus 1 to the 4/5, which means we have 5/2 times, what's b going to? Infinity. So what's infinity to the 4/5? Infinity. And beyond. Thank you. So that's going to become, or give us an answer of infinity, which means basically this is divergent. This has effectively, no real solution. There is no real solution. And I like writing the answer of infinity, but it also means that that improper integral is divergent. There is no real solution. Okay, so our last example, we started this class off with a little AB review. So now, let's see if you recognize this problem. Another review question inside of new material. We've got, for our last example, we have the definite integral from 0 to e squared of the natural log of x cubed dx. What, oh, that was a nice face. What do we need to do first before integrating natural log functions? Rewrite them. You want to expand them. And actually, I said integrate, but we don't really, we're going to have a little bit of an issue. But when we were taking derivatives of natural logs, I always said before you take a derivative, expand those as much as possible. So we can bring this, and what do you get from a logarithm? Exponents. So the natural log of x is an exponent, and that is raised to another exponent. So the power property will let you bring the 3 out front, but that's going to be a constant coefficient, so I'm going to put it out in front of the definite integral. So we have 3 times the definite integral from 0 to e squared of the natural log of x dx. What's the integral of natural log of x dx? Come on, you memorize all those rules. It was like 17 or 18 integration rules. What's the integral of natural log of x dx? Oh, we don't have a rule for that. So if we cannot directly integrate the natural log of x dx, maybe for this example we might want to, we can leave the 3 in or out, but I think maybe since we haven't seen one of these in a long time, or maybe never, I don't remember if this is in your homework or not. Did we ever integrate natural log of x in the homework? So a couple of you were saying yes. I don't remember exactly what was in this homework involving this topic. I'll put the 3 back in because it might help you with the rest of this. It might not. I don't know. We have 2 problems with this. One, reminded us that we can't directly do the integral of the natural log of x dx. And secondly, while there are no infinities in the lower upper limit, this is actually another improper integral. On the closed interval from 0 to e squared, is the natural log of x continuous? Is this function natural log of x, or 3 times the natural log of x, is that function continuous on the closed interval from a to b? No. Why? Yeah, the natural log of x has a domain that x is greater than 0. The graph of y is equal to the natural log of x has a vertical asymptote of x equals 0. So though we don't have an infinity in one or both of these locations, we do still need to recognize that this is going to be an improper integral. The end of our closed interval is where the asymptote is. So if we're finding some area between a curve and the x-axis, maybe that some of that area is just going to, like, you know, escape out of this asymptotic behavior and just give us give us a value of this definite integral, which is infinity or negative infinity. So how we fix that is with the same notation we did with the previous question. We're going to do the limit. We're going to put a constant in this lower limit that's not 0 and not negative. So we have that continuous, or we have that closed interval for which this integrand is continuous. So we're going to go a to e squared of 3 natural log of x dx. And then we're going to let a approach what? 0, not infinity, but 0. And are we approaching 0? I shouldn't have erased that graph already. Are we going to approach 0 from the right or the left? We're approaching 0 from the right. So we have the limit as a approaches 0 with a little plus sign in the exponent location. The limit as a approaches 0 from the right of the definite integral from a to e squared of 3 times the natural log of x dx. Now, there is a way, and I hope I don't mess you up with this, there is a way to write proper notation for the process we're about to walk through when it's a definite integral. I just don't like using definite integral notation with what? What are we going to have to do to integrate 3 times natural log of x dx? Woo! Oh. You looked away, snap in the forehead. Integration by parts. So we're going to let, let's put over here. We're going to let v, or u, yeah, u. We're going to let u equal the most complex part of the integrand that when we take a derivative becomes simpler. Or we use a liate. So what factor, what function do we take a derivative of and it gets easier? Natural log of x. So u is going to be the natural log of x. And then du is going to be 1 over x dx. Nice job. And then dv, if I left the 3 out front, dv would be 1. I put it back in just so there was another function for you to look at. But dv is going to be 3 dx. And then v is the integral of 3 with respect to x, just to show that notation, or it's going to be 3x. And let's not forget, it is the integration by parts is the integral of u dv is equal to uv minus the integral of v du. So the indefinite integral of 3 natural log of x dx is going to be equal to u, which is the natural log of x, and v, which is 3x. So we have 3x natural log of x minus the indefinite integral of v, which is 3x du, which is 1 over x dx. So actually our variables of x are going to cancel out. We can bring the 3 out or not. What's the integral of 3 with respect to x? Of course we know that. We're in BC. 3x. So we have 3x natural log of x minus 3x. Now it's plus c, but we're doing a definite integral. So our next line of work here is going to be the limit as a approaches 0 from the right. We have, from our indefinite integral, we have 3x natural log of x minus 3x with an upper limit of e squared and a. Now you guys always do a good job of checking my answers, but There you go. So we have now the limit as a, not x, as a approaches 0 from the right of 3e squared natural log of e squared minus 3e squared minus parentheses. Now we're going to plug in the a. We have 3a times the natural log of a minus 3 times a. Okay, so what do we have? The limit as a approaches 0 from the right. Well, just for some practice, what is the natural log of e squared simplified to? Log base e of e squared just becomes 2. So we've got 2 times 3 is 6e squared minus 3e squared minus 3 times a, which is approaching 0, times the natural log of a. Ooh, now hold on a second here. The natural log of a. That's approaching negative infinity. Minus 3 times 0. Well, we've got ourselves a little bit of a pickle. The limit as a approaches 0 from the right of a times the natural log of a is in the form of 0 times negative infinity. That's actually a form of indeterminate. And it's not a form of indeterminate that we had to learn. So I wrote this example for just calculus in general, not AP Calc. But let's go ahead and finish it. We are going to need to evaluate this limit using L'Hopital's rule. But to apply L'Hopital's rule, your form of indeterminate needs to be either 0 over 0 or some kind of plus or minus infinity over infinity. And 0 times negative infinity is a form of indeterminate, but I actually never needed to give you practice on this. So let's see here. A is going to 0. And the natural log of a is going to a negative infinity. So I need to create a division to get this to be either a form of 0 over 0 or infinity over infinity. So the natural log of a is always already going to infinity, so I'm going to take this multiplication of a and write it as a division of 1 over a. So this is going to become the limit as a approaches 0 from the right of the natural log of a over 1 over a. And now College Board AP really wants you to write, when you're doing your condition checks for L'Hopital's rule, to write a limit statement for the numerator and a limit statement for the denominator separately. Because we're already at the end of a long video and this is kind of a complex question, I'm not going to say this is equal to, because that would be wrong, but I'm going to say that this limit is now in the form of, because of the graph of natural log of x, what that looks like, we know as we approach 0 from the right, the natural log of a is going to go to negative infinity. And the denominator is going to be 1 over a denominator getting ever small is going to go to positive infinity. So we now have the form of infinity over infinity. So we can apply L'Hopital's rule. And we get the limit as a approaches 0 from the right. What's the derivative of the numerator? What is the derivative of natural log of a with respect to a? 1 over a. What's the derivative of a to the negative 1? Negative 1 over a squared. We have the limit as a approaches 0 from the right. This is going to have to be what? When we flip up this division of negative 1 over a squared, we'll have negative a squared, and negative a squared divided by a is negative a. So the limit as a approaches 0 of negative a is what? 0. So we didn't, it would be incorrect to say 0 times negative infinity is just 0. That is a form of indeterminate. So this second term all just comes out to be 0. And then we have 6e minus 3e squared is equal to 3e squared. This is a finite real limit. Thus, the original question was, what's the definite integral from 0 to e squared of the natural log of x cubed dx? Even though there's asymptotic behavior, even though this function is not continuous on the closed interval, in this particular case, we do now know the answer is 3e squared. Bam! Woo, that one was, in my mind, because so many limit statements, when we learn L'Hopital's rule goes to infinity, I kind of stopped looking at what I was doing, and I doubted myself because I wrote what I wrote in the iPad is wrong. My brain started saying, well, if a goes to infinity, this answer is going to go to infinity, and I knew there was a real solution. So, and then you said the derivative of natural log of a was 0, which if a was a constant, it would be, which is what I wrote on my paper. So I really got all of a sudden I was like, I glitched there and I was like, wait a minute, something's really wrong. But that was what happened. And that, it wasn't going to go out to infinity because we were letting a be approach 0, not infinity.